Then for the next talk, Matthis Kruse will talk about composition of spectre mitigations. Go for it.
Okay. Yes. Hello, everyone. As introduced, I'm Matthis, and I'm going to talk with you, or to you, about the CQ composition of spectral mitigations, which is joint work with Professor Michael Backes. So, well, you've seen it one talk earlier, but for sake of self-containment, let's refresh ourselves about this speculative execution example. So we have a simple bounce check program and some kind of array access that uses this index, right? Now, if you suppose that that index is, for example, 1337, and the size of the array is actually just 64, well, then clearly the bounce check is false. However, branches are typically rather slow to execute, so modern processes do speculative execution, and you would speculate here on the fact that the condition is actually true, and start to actually load the value that is at that particular position. So clearly way out of bounds and just some random garbage, and well, at some point the processor may notice, well, okay, that guess that this branch is actually true was wrong, and roll back. And so this rollback operation, unfortunately, is done in a dirty manner. Stuff is left on the cache, which an attacker could exploit. Okay, so much about that. You can, for this particular example, introduce a barrier operation, which just says, okay, if you start to speculate, then just stop here, right? Just stop speculative execution and wait. So there is a mitigation technique to overcome certain speculative execution vulnerabilities, and there are many such vulnerabilities, and even for a single vulnerability, there are even there are a plethora of other mitigation strategies. So I've shown you this strategy where you just insert a barrier, but it's a very slow strategy because you just say, okay, just don't speculate at all. But speculation has been introduced to, well, improve performance. Clearly not necessarily the best strategy. And also we may be interested in, well, I mean, this is a big graph, right? And we do formal methods. And typically you are interested in doing this in a kind of modular fashion. If you tackle this globally, if we have like one compiler pass, for example, that makes sure that there is no speculative execution vulnerability that does this in a monolithic manner, then this is clearly not so desirable. And also in practice, compilers are developed in a, I guess, modular fashion. So if you have a very simple compilation pipeline where you start with a blue program and you would translate this to a kind of, in this case, intermediate representation in red. Of course, in practice, you perform some kind of optimizations, analyses, all this funky stuff. And at some point, you lower to your target language. And from my point of view, or from this talk's point of view, these compilers are just compositions of smaller compilers. So we can view a compiler as several smaller compilers put together. And, well, if you now consider that maybe this one, this compiler A and this compiler B are secure, one question would be whether the resulting pipeline is secure again. And unfortunately, this does not necessarily hold in general. So one example of this is as follows. Let me first give you an example where we have a desirable compilation pipeline where it works. So here we have a read operation at a particular memory location and some particular index, which is potentially out of bounds. Now, if we have a compiler that introduces bounce checks, we would introduce a bounce check for each memory operation. So again, a very stupid countermeasure because we could optimize this somehow, but for the sake of this example, we introduce a bounce check for each kind of memory operation. And in this case, this bounce check is again false, and we again have the speculation with a potential leakage of the value. Now, if we compile this program further using this barrier compiler that just introduces a barrier after each branch operation, right, completely disabling speculative execution that way, we essentially end up with a program trace that does not contain the leakage because we have the barrier when we start this speculative execution. So we end up with a secure program, at least with respect to that particular kind of speculative execution vulnerability. However, if we now swap these two compilers, so if we first introduce barriers for each branch and then introduce bounce checks, we are kind of screwed in the sense that the bounce check compiler introduces the bounce check, but this branch is now not secured with a corresponding barrier operation, right? So the compiler tried to enforce memory safety in that sense, right? To make sure that you don't have out-of-bounds accesses, but in doing so, introduced another vulnerability, which we don't want to have. Right, so the goal of this work, the goal of this talk is to provide a formal analysis of the compatibility of different kinds of these compiler mitigations, right? So first up, let's maybe refresh ourselves what a secure compiler actually is. And for that, I go a little way back and talk about correct compilers. And I'll make it quick, don't worry. So from the perspective of this talk, a correct compiler is just, the statement where you have a whole program execution at the target level, and essentially the compiler needs to preserve the property satisfaction. So we have any kind of property, for example, memory safety, and the compiler has to make sure that if that property holds in the source, it should also hold in the target. But clearly, compiler correctness in that fashion is not necessarily practical, because in practice you would write programs that are not whole, meaning they have holes, they have undefined symbols. If I write a simple C program that does printf, that reads from standard input, I need to link to the C standard library. So I rely on some kind of assembly blob that I link after compiling the C code to provide me with these missing definitions. And this is captured in the well-known robust preservation statement, where you just quantify over partial programs instead of whole programs, and contexts which you link with this partial program. So this exists in literature, and this is our notion of compiler security for the sake of this talk, also known as robust preservation or robust trace preservation. Okay, now we've proven in earlier work that you can compose this actually. So if you know that you have a compiler that is secure, so robustly preserving a class of security properties C1, and you have another compiler that is robustly preserving with respect to a class of security properties C2, then you can compose them together, run them in sequence, and end up with a compilation chain which is secure with respect to the intersection of these two classes. But again, in practice, even if you have a very, very simple compiler, namely the identity compiler that just performs a recoloring operation, so we have very similar programming languages, the blue and the red are syntactically equal, however, they differ in one way. The blue language does not have speculation at all, and the red language does have speculation. So even for a simple compiler that essentially does nothing, you end up with different traces in the source, or different trace models in the source and in the target language, right? For example, with the bounce check program, in the blue language where I have no speculation at all, I would perform the bounce check, potentially see its faults, and that's about it, because there's no speculation. But in the target language, I would perform the speculative execution and have the leakage. Right? So clearly there needs to be something done with respect to the compiler security statement. And this also has been done already. So essentially what we want, for example, we have this property that we don't want to have any leakage whatsoever at the target level. And what we essentially want is to translate this to a source level property, or rather, if we already have a source level property, translate this to a target level property. So we have two kinds of functions that also are in a, form a Galois connection. And they are parameterized over a cross-language trace relation, where you say, okay, this blue trace should be equal to this red trace. And this really induces these kinds of mappings, where I can go from a red property to a blue property and back again. For the sake of this talk, we are only interested in this projection, where we go from red to blue. So from target level properties to source level properties. And we changed the statement accordingly. So instead of having a black trace, now we have a blue trace and analogously a red trace. However, we also quantify over target level properties. And well, for the blue trace to somehow you need to say, okay, this blue trace needs to be in the projected version of this target level property. And we've also proven that this composes. So if you know that you have two compilers that are secure with respect to certain security classes of properties, then you can compose them. The crucial bit is that the first compiler that you have in your pipeline, or like in this two-compiler pipeline, needs to be secure with respect to a projected version of the first property, which can I zoom? Yes, I can zoom. Nice. Which makes use of this relation that represents the semantic effect that the other compiler has. So the compiler that we run after the first compiler is run. Right, and if we go back to the example where we first run the bounce check compiler and then the compiler that introduces barriers for each branch, then we remind ourselves that if we run it in this order, then everything is fine. But if we swap the order, then we get into trouble. And we get into trouble because if we want to make sure that the compilers the whole compilation chain is secure with respect to a property that says, okay, there should be no speculative leak whatsoever, at least with respect to that variant. Then if we project this to an intermediate level property using this bounds relation that represents the semantic effect of the compiler that introduces bounds, meaning essentially equating this red trace with this green trace, then we are in a sense screwed, because we can find an intermediate level trace that is related to a target level trace that violates the property that we do not want to violate. And you have to make sure that this does not happen. So you have to make sure when composing that you cannot come up with an intermediate level trace that somehow is related to a target level trace which violates the property that you want to make sure to not violate, right? Yeah, so the overall goal of this work essentially is to make several proofs about compositions, about these compiler compositions for different speculative execution mitigations. So for example, if we start with a completely insecure program with respect to speculative execution, then we may apply the barrier strategy or this index masking that Xaver mentioned earlier to obtain a program which is secure with respect to the SPECTRE variant v1. And I presume that you can apply index masking and the barrier operation again on a program that is already secure with respect to v1 and still obtain a program that is secure with respect to v1. And yeah, we kind of want to expand this graph further. If you now apply this barrier compiler again to make sure that the SPECTRE variant v4 cannot be exploited, then I envision that in the end you get the combined version of v1 and v4, again can repeatedly apply the barrier operation. But for example, if you now apply the index masking, then the v4 variant may break, right? And so on and so on. So the final goal is to really, the final goal of this work is to really prove this graph, to make sure that, okay, I know really what compilers I can compose to end up with a secure program and to know what kind of security statement I have. So for example, I know that I can start here and just like go this path maybe. Okay. Yeah, that's already it for my talk. So thanks a lot. Do you have any questions?
questions? Yes, Peter.
So how many distinct subsets of protection do people out there in the world want to use?
That's a good question. I'm not a person that is out in the world, so it makes sense to make sure what subsets they are interested in, right? I cannot faithfully answer that, unfortunately.
So, do I understand correctly that the goal of this work is rather similar to the previous speaker? And if so, can you compare? And
Sure. So we've done this composition framework in earlier work. And what we now want to do, which, we can use the earlier work for this work as well. But it differs in the fact that the framework that we have here is a little bit more generic in the sense that you talk about the composition of these compilers, and the earlier work was more focused on specifically speculative execution variants. Whereas here you could really have any kind of property whatsoever that is expressible by means of program behavior, namely events, sets of traces, and so on. Yes, and this is a mere instantiation of that framework, basically.
Also, this work is really about composing compiler passes, whereas Java's work is a single compiler pass. How strong a guarantee can I get for that single compiler? Now, of course, there's synergy between the two, right? Like Java's results can be reused in Matthis' results, and Matthis' results, in a way, they fulfill some of the well-formed composition assumptions that Java needs. But there's one is for multiple compilers, one is for single compilers, for example.
I have a question.
Yeah.
Are you planning to use like a proof assistant to formalize this theory and compose things, or do you have any ongoing work on that with that?
Yeah, so parts of the existing theory with regards to the composition, or rather the core composition theorems, so let me go back to this one. That one. That is formalized in Coq or in Rock. However, of course, you need to provide a secure compilation proof for the particular compilers. And in order to instantiate this framework, you need this, or kind of need to assume this at some point. And there are not so many practically relevant compilers that are formalized in the proof assistant, right? So, it's somewhat open whether we can formalize everything. But I presume at least the core theoretical work can be formalized in Coq.
Right. So one thing that like I've always feared with respect to modeling speculative execution and proof assistant always like seemed like super hard to me. So like, it would be very cool like to have some of that, I think. Especially not only speculative, I would say, but in particular out of order.
Yeah.
Because I feel like you need to keep a lot of like the reasoning about like out of order execution. You need to somehow keep on the side a lot of invariants about, I don't know, like your configuration can still step and like, so yeah, would be interesting to see that happening. Dominique, one more.
So I'm curious how you see this fitting into a full compiler pipeline. So I guess this is the sort of thing that you would have to do all the way at the end, but I mean, is that feasible because you still have linking going on afterwards and maybe dynamic linking and so which sometimes inserts weird code that does sort of lazy loading and whatever. Have you thought about that at all? Or?
Yeah, I mean, in the end, it boils down to the question of how practical the robust preservation statements are in that sense, because the composition framework here really relies on them. And if you can model a practically relevant compiler and prove it to be secure with respect to these kinds of statements, then I think it's totally feasible. But of course, we don't really have like a really production-ready compiler that is formally proven secure with respect to this kind of statement.
Sure, but how do real compilers do this? Do they do this red Pauline, for example? Do they do that in the backend all the way at the end in the backend, or how do they prevent like very late optimizations from breaking the properties again? And
Yeah, good question. From what I understand from the community that is interested in making sure that cryptographic constant time really holds in the end, for example, is that people still tend to insert inline assembly or like annotations that make sure that, hey, compiler, just don't touch this and just translate this one-to-one. And I guess people in the speculative execution community do similar things because there is an overlap between them, right? Both are likely people that are interested in developing cryptographic libraries, for example. But yeah, it's a bit outside of my practical expertise, to be honest.
Oh, one more question there.
Oh, do you want to?
No, please.
Yeah.
So great talk.
Thank you.
Usually one of the nice things about sort of these vertical compositionality proofs is that you can do that proof independently of that proof, right? That secure compilation proof independently of that secure compilation proof.
Yeah.
And in this diagram, that's not exactly the case anymore because now that little sigma over there, right, is somehow dependent on that second compiler.
Yes.
And I understand that's sort of maybe just an inherent difficulty in certain situations like this, but I'm wondering if there's any relationship between that, the unadorned class C1 and the projected class with the sigma. Like if I've already done the work of proving it secure with respect to C1, do I gain any benefit now when I go and I try to prove this modified class, or is it really like I'm starting from scratch? Or does that depend very much on what sigma is?
It depends very much on what the class of security properties is, and it depends very much on what the trace relation that sigma uses actually is. So sigma is a set thing that is constant, so to say, but it relies on this cross-language trace relation, which kind of is induced by the compilers that you use in your compilation chain, right? They describe the effect that the compiler does. For example, for the bounce check compiler, the cross-language trace relation would say, okay, I associate each memory access with a sequence in the target that says, okay, I have to do a bounce check first, right? And then potentially perform the memory access. So clearly there is some overlap, but I have yet to really get into the details to see it, like in a concrete instantiation of this, how difficult or how proof reuse actually happens in that sense. Yeah.
Thank you.
Okay, let's thank Matthis again.